Alright, so recently I have been thinking about matrix multiplication, dot products, scalars, in terms of linear algebra, all that bullshit. It's weird that, so we have like matrix multiplication, right? Which, let's pop this up to something like that. Let's do all prime numbers so you can see where everything goes. Where are we at? 17, 19, 23. There's a 3 by 3. Let's do let's do that. Sure, just prime numbers. Alright, so now, if we multiply these guys, what happens to that result? This is a 3 by 3, this is a 3 by 2. We can change this to, right, something like that. Okay, so the number of rows in the first one is the same as the number of columns in the second, in the result. Right, blah. The number of rows in the first one is the number of rows in the result. The number of columns in the second one is the number of columns in the second one. There we go. I understand how words work. Alright. So, columns, columns, rows, rows. That's what's happening. Now if I swap this, totally different result, right? So here's A times B, it's a 2 by 2. Here's B times A, it's a 3 by 3. Okay, that's basic matrix multiplication. But now, how do dot products work? Dot products take what are called column vectors and multiplies them together. Notice that doesn't work. It throws an error. It's like, we can't do that. We don't know how to do that. So dot products have to be explained completely separately. There's a very deep problem with this. Apart from the obvious fact that we should be able to explain it. We should be able to, if it's matrix multiplication, because, right, these are obviously matrices. These column vectors are obviously matrices, and a dot product is a multiplication of matrices. We should be able to do this. But there's something deeply wrong with what's happening here. Also, the result of a dot product is what's called in linear algebra a scalar, which is an appropriation, a misappropriation of the term scalar, which occurred in the mid to late 1800s. Originally, what a scalar was, well, originally there was no term for this because it was simply what Euclid and all like ancient Greek mathematics called multiplication. What a scalar was to Euclid, who didn't need this word because why would you need this word, was simply when you multiplied by a magnitude. And a magnitude is unsigned. It is simply like 17 or pi or something like this. It's an unsigned It's not positive, it's not negative, it's unsigned magnitude. That's it. And when you multiply by that, you get a scaling. Okay? The problem that occurred in the 19th century, in the 1800s, is this term, well, okay, in 1600s, I think it's like the 1570s or 90s or somewhere in there, it's somewhere in the 1600s. I think he was French, I don't know. This guy actually invented the term scalar for this meaning, and this is exactly the meaning that he gave. It's like when you multiply by a magnitude, that's a scalar, right? The thing you're multiplying by, let's call that a scalar. Okay. So he defines this term, and it's just synonymous with Euclidean multiplication. So there's a reason that this wasn't a word before. But that's all it's doing. And then come the 1800s, and suddenly, like, we're working with matrices and linear algebra is developing and abstract algebra is developing and all of this. And they just kind of adopt this word for things that are not matrices, which is completely different. This is a completely different meaning for the term. Alright. So now it can be signed. It could actually even be complex or something like this, right? Like, it could be, and by the end of this development of the redevelopment of the term scalar, it could even be a matrix. So you completely destroyed what this fucking thing means. Right. But there's a reason that it was called scalar in the first place, that this, just multiplying by a bare, unsigned magnitude, is a scalar, and this is different from other transforms. So, if you multiply by a bare magnitude, an unsigned magnitude, okay, you can make something bigger or smaller. So, right, so say we have like in Euclidean geometry, say we have a figure that we have drawn on our planed surface. Alright, so it's a flat plane. It's not fucking spherical or hyperbolic or whatever, because we've read Euclid and we understand what he said. And he defined that our working surface is a planed flat surface with edges, because it's a real surface. It exists physically. So it does not extend infinitely, right? So when we look at this, we can see that this violates what is now considered to be Euclidean geometry, or Euclidean geometry violates what Euclid actually defined as what he was doing when he was doing geometry. Anyway, so if a figure drawn upon this, we can scale it, right? So we can make it bigger or smaller, and independently of this, we can also move it around. Okay. Now, if you were to multiply by a negative, that induces a reflection, which is different from a scaling. And this, so if you multiply by a negative, you invert the chirality of the figure. So if it was, say, right-handed, in some sense, if you multiply it by a negative, if you quote-unquote scale it by a negative, you get the left-hand version of it. That is not a scaling anymore. That involves a reflection. So this multiplication that you did was not a scalar. It was not a scalar multiplication. Okay, so this is a big problem. Because now, post-1900, scalar allows us to do this. So the meaning of the term has been completely lost. It's not scaling. It's doing like any random geometrical transform now, pretty much. So that's a problem. So the term scalar, as it's now used, doesn't mean anything. It's gibberish. It's just nonsense. Okay. But also, if we look at these, so if this is a column vector, okay, the idea here is that these are different variables. So this would be like 2x, 3y, or just, you know, xy and Z. These are supposed to be different dimensions from each other. But, let's play with this one. The entire point of columns is to distinguish your dimensions. Oops. Come on. There we go. So, the entire point of columns in a matrix is to distinguish your dimensions, right? And this is how a system of equations works. This is why matrices were first developed, is to work with systems of equations to distinguish your variables in the columns. And the rows are interchangeable, right? So this is literally an ordered polynomial. A row is an ordered polynomial, and a column is an unordered list of ordered polynomials. So, what should really be happening here for A as a column vector is it should be like this. No. It should be like this. So we don't need the variables anymore because you can tell what's happening. So if the 3 is a different unit than the 2, then it needs to be here. And if the 5 is a different unit from those two, it needs to be here. Alright, now watch. Watch what happens to our B by A when I fix this. So get rid of that. That. Let's do, where are we at? Let's do a 7. Oh, we're getting a multiplication now. 11, 13. Look at that. Now, the multiplications work, and just like a dot product is supposed to be, it's commutative. B dot A is the same as A dot B. Boom. And the output, now the output at this point looks like the same as this. Now this is an expanded column vector, so this is also an expanded column vector. Now if you're at all familiar with Cramer's rule, this is now going to make a lot more sense. If you plug this in for the column vectors that you see in Cramer's rule, this explains everything much, much nicer. But now, there's still something missing, because this isn't what we're expecting from a dot product. The dot product is this. There's your dot products. And now you can fully explain what a dot product is with respect to matrix multiplication. And we can also explain what column vectors are. Mostly they're a misunderstanding of what the fuck is going on. And this shouldn't be surprising, right? Because, so dot products are sort of like the holotype, the prototype, the stereotype of inner products. And the concept of inner products was developed primarily by Giuseppe Peano, who is, if you are in any way familiar with his career, he was absolutely an intelligent man. He noticed a lot of things, but he was extremely non-rigorous in his development of these ideas. So he noticed this works, but he didn't understand what the hell he was doing. So he described how to do it, and that spread like wildfire. But nobody ever came back and was like, but why does it work? Nobody ever fucking looked at it from that point of view. So in modern mathematics, if you're working with matrices, we end up having these two completely different kinds of multiplications that you can't explain relative to each other. And nobody really questions this because it's such a heinous, like, hazing ritual to learn this that nobody really wants to revisit it. Like, this is kind of, I think this is what's happening. So if you're to the point where you understand it, you don't want to revisit it and try to figure it out and explain it to anybody else. I'm pretty sure this is what's happening. like any sort of religious doctrine, like because it makes no sense, nobody wants to go back and try to make sense of it. So nobody does. And we just get this constant pushing forward of, well, this thing, this description here is working for us, so let's just keep going with that and don't worry about the why. The problem with this is all considered to be rigorous when it's absolutely not. Because if you don't know why you're doing anything, couldn't you be doing something else? Like, why is this the thing that works? Why is this the thing that we picked out? The whole point of rigor is that it constrains us to one option, right? If you don't understand how matrix multiplication and dot products relate to each other, how you can derive a dot product from matrix multiplication, it's non-rigorous because you have these two random options that behave completely differently as far as you can tell, right? If the columns and rows of your two input vectors are dictating how the output behaves, and the number of columns of your initial matrix in the multiplication gives you the columns, or the number of rows in your input gives you the rows in the output, and the columns in your second one gives you the columns in the output. Fucking, it's so ridiculous. It's even worse than this. Then it's impossible, and so the number of columns of your first one has to match the number of rows in your second one. It's impossible to multiply column vectors by definition because they have one column but multiple rows, so you can never get that alignment correctly. But also the different dimensions in your column vector don't even make sense. So column vector doesn't even make sense unless every entry in your column vector is actually a multidimensional polynomial, in which case it's not a column vector, it's a normal square matrix. What are we doing? That's what these are, right? This is what happens when you expand this out. You take your column vector 2, 3, 5, and you expand out the polynomials in each row. You get this square matrix. And now you can multiply them and commutatively, right? B times A and A times B ends up being the same thing because really all that happens is we're looking at this diagonal here. And so this is part of why this is some bullshit. That second matrix in your multiplication, I think we're all fairly convinced of this at this point. So here, let's do this. Let's do A. Okay, now A times A transpose. Alright, right now the transpose of A is the same as A. Alright, so what it's basically doing is you're getting 2 times 2 here, 3 times 3 here, 5 times 5 here, 4, 9, 25. Watch what happens if I put something else in here. Okay. Now, okay, so now the transposes are different, so if I move those, it changes it, right? But if we look at what's happening under the hood with A times A transpose, it turns out we don't need to know anything about A transpose at all. Because what we're doing is we are multiplying row column. But when we take the transpose, it just ends up being row by row. So we end up being able to just we can describe everything with just that. I mean, that's not how you. Something like that would be enough to convey this. That's enough information right there. A times it basically itself. Right. So there's all kinds of weird problems in here. You have, so if you're multiplying two things together, it should be necessary to know what both of those things are. But with matrix multiplication, because of the way that it's defined, you don't really need that necessarily. A times A transpose is a different thing from A. Except you don't need to know anything about A transpose. You never need to look at that at all, ever. You can do A times A transpose just from A. And not in the sense that you're deriving A transpose from A. You literally don't ever need to consider A transpose. You never need to consider anything that's any of the differences between A and A transpose in order to do this. Which is fucking crazy. Right? So this leads into this other problem that what is happening is matrix multiplication is not actually matrix multiplication. So here, let's call this first argument. We'll say that this is behaving as a matrix in your multiplication. Okay. The second argument is polynomialized. What's happening is you're taking the transpose of it, and then you're compressing, you're doing the opposite of this, what we did here. You're compressing this expanded polynomial into a single entry, and you're multiplying that term-wise into the other matrix. So really what you're doing is you're multiplying a matrix by a column vector of polynomials. Which is why it's non-commutative, because the second one is the one you're polynomializing. The first one you're leaving as a matrix. So if we swap the order, it's going to behave completely differently. But if we notated somehow that that is what you're doing, then it would become commutative. So this would now be true. And Desmos has no idea what I'm talking about right now. But you gain this sort of commutativity when you notice that what we're doing to this one is we are polynomializing it. It is now equivalent to the reverse order of it. But because nobody who's doing any of this shit actually understands what the fuck they're doing, nobody's noticed this apparently. And you can see this when you look at things like the fact that bracket notation even exists, right? The fact that so matrices are written conventionally with capital bold letters. Column vectors are written with lowercase bold letters, even though a column vector is just a data compressed square matrix. And when we have bracket notation to indicate when we're working with column vectors instead of matrices or quote-unquote scalars, which are not scalars. Nothing about any of this is rigorous, right? It works. The notation is in many regards convenient, sure, because if we're gonna data compress this into a column vector, right? So it's just 2, 3, 5. Like, why write the zeros? Like, that makes sense in terms of data compression. But in terms of actually understanding what's going on, it's important to realize that that column vector is synonymous with this square matrix, and it has to be, in order to distinguish the units on each of these entries. You cannot distinguish the units of the entries on a column matrix by definition, right? A column matrix is an unordered list in the same dimension, in a single dimension. It's an unordered list in a single dimension. A row matrix is a polynomial, so it's an ordered list across multiple dimensions. Each entry is perpendicular to every other one. We don't know the relationship between the entries in a column matrix, but the way that conventionally we're using a column matrix, we're saying that they're all perpendicular to each other. Right? This is non-rigorous. You just kind of made up some shit for the sake of convenience, which is exactly the sort of move that Giuseppe Peano would do. This is absolutely fits his MO. And the fact that he's pretty much the one that established this, that makes absolutely perfect sense, right? In a sense, it's not wrong, but in another sense, it's absolutely everything about it is wrong, which just completely fits Giuseppe Peano. Everything he does. The successor function mapping to the naturals is exactly like this. Yes, you can get the successor function to map to the naturals, and this is not useless, but that is also, it induces, if you're trying to make that your foundation of mathematics, this induces all kinds of paradoxes because it's non-rigorous and it fails to note a whole bunch of other things that are going on, right? So this fits Peano's MO perfectly. The problem isn't the way that this was established. The problem is that nobody ever looked at it and actually made it genuinely rigorous. Nobody ever looked at it and said, hey, look, we could just derive dot products from matrix multiplication, noting that some of these things, these are just convenient conventions to reduce the amount of writing that we have to do, right? Like, so the whole point of a column matrix, of a column vector, which we should notate differently than a matrix, right? The notation for the way that you write a column vector is the same as a matrix. But it isn't a matrix. It shouldn't be. Right? Because it's data compressed. And now when you have this dot product between these two column vectors, it's commutative. It's naively abelian. Right? You don't have to do anything like this, like note your units here. Right? So B is being manipulated in a way that changes what it is. And that is a part of this multiplication that it's just classically just absorbed as part of the operation. So like you go around saying, oh, it's rigorous, but really all you did is you randomly defined your operation in the wrong way. So that it's taking on a bunch of the syntax of what's going on. When it's shouldn't be doing that. If it's a proper verb, it shouldn't be carrying all of that syntax. It shouldn't be doing all of that work, right? Particularly if you want to marvel at it and be like, oh, look, it's abelian. Why? Or it's not abelian. Whichever one. Why is it not abelian? Or why is it abelian? Well, because you defined it that way, dipshit. You defined it like it's included in the definition of your operator, which there's so many things wrong with that. And now, when it's done this way, this is literally the same as arithmetic multiplication. The same arithmetic multiplication that we can, when we understand it correctly, gives us calculus. It's the same exact thing. We don't have to define it separately, right? And we don't have to define dot products separately, right? So now instead of having 4 completely different senses of multiplication, where you've got the arithmetic multiplication, integration in calculus, matrix multiplication, and dot products, and this is not to mention things like cross products and whatever. There are more. Instead of having these 4, so we'll just talk about these 4, right? So you've got arithmetic multiplication, integration, matrix multiplication, and dot products. Instead of having them all separate, because we're just defining them incorrectly all along, instead of having 4 distinct things, they're all completely unified into one single thing. That's rigor.